Okay, so the last time, we were talking about flatness. Let me remind you, very quickly. Flat. If we're all coordinate sequences of harmonics. Given any shortage that sequence of harmonics like that, then the induced sequence zero into the C so another way to think of this is, let me make this mark. So whenever you do this little business here, we already know from tensor product that in this situation, if this is exact here, then this is exact, right? So really, what does it mean to be flat? It means it preserves one-to-one maps, right? Mark. You know, if and only if we're all harmonic homomorphisms. Yeah, from A to B, we're all one-to-one, our module homomorphism A to B. Homomorphism F tensor 1M is also one. So what it means to be flat is it just takes care very nicely of homomorphisms. We know that recall one of the results we had to prove last time. If F3, say, I'm going to write it this way for convenience. So F is isomorphic to this. Let me point out that that A tensor R this is isomorphic to this is a result we used last time, and you can bootstrap this result to show that any free module is flat. And in fact, some people consider flat to be, sort of, slumming and free in a certain sense. It's kind of a nice generalization of free. If I could generalize projective. If you look, one of the big things about free modules is well, you have a basis, right? I mean, that's the big thing. It's got a non-empty basis, and essentially that's reflected here. The number of copies of R is the number of elements of the basis. There is a characterization of flat, an element-wise characterization of flatness in the Borbach P, where flat modules have something that's close to a basis. It's not exactly a basis, obviously, because then it would be free in general. But flat modules have something that's close to a basis. Let me give you the theorem that shows you the kind of the big pecking order. And in the next homework, I'm going to have you pick apart some of this anyway. We're gonna talk about, I use the next exercise to kind of hold your hand a little bit, take you through some of the flatness. Let M be an R module. We have the following implications. A minus B minus C, and none of them are reversible in general. Number one, M is free. Number two, M is projective. And number three, um, let me go through this a little bit. One plus two is done. We already showed the how much we show that projective implies glass? Well, let's suppose. Um, let me say. Well, so I guess I'm gonna skip that now. Exercise, but let me talk about the non-reversible. Um, I'm gonna tell you this out, and I want you to prove some of this, because I know, in fact, this one's homework. First of all, for this one, I don't think we ever discussed it. So we know that free and positive projective. Can anybody take an example of projective R model that's not free? All right, I mean, maybe I've just been kidding you guys all along, right? Make up these definitions just for the heck of it, all the same. Well, there are some rings, in fact, principal ideal where you don't want to look, because we're going to see a theorem after business that any any, any projected module, yeah, the is packet free. But let me give you a start. See, come on. What are some characterizations? Well, I know what a free module is. It's just a direct some number of copies of the ring, right? What does it mean to be projected? Right, there's the diagram, that's the definition, but with respect to free, what's the relationship? The module is projected if and only if it indicates the direct sum of free. Remember that one. P is projected if and only if you can find another module cases and P some cases. D6 is a free. D6 module. Basically it's generated by one. This is true for any ring, right? That a ring is a free module of itself, basis one, right? One times something is E6 equals 0 means that that thing has to be 0 bar. Anybody decompose E6 into a direct sum, or direct sum, I should say. Right, I'm gonna write it out specifically. It's the internal direct sum. As you say, right? Because notice the intersection of these two submodules, and these are, of course, these 6 submodules. The intersection of these two are 0. And I know that when you put them together, you get the whole thing because, for example, 3 bar plus 4 bar, 1 bar. So you've got 1 bar in the sum. So you got everything. Now, what's the significance of this? Well, Z2 and Z3 are summons of G6. So they're projected. That means they're summons. But they are not free themselves. And this is counting because if F is a free Z6 module, then the cardinality of F is infinite, or that's finite. What was the cardinality of any free Z6 module be? Well, it's a finite number of copies of Z6, so I don't know much, but it's gotta be a power of 6. Fine. And I don't know much, but I do know that 2 and 3 are not powers of 6. Right? So they're not free, but there are some of them free. So they have to be projected. Any questions? This is trickier. Anybody know, does anybody know what flat module is? Not projected. I'll give you the example without proof because this is the part that I know here's a number. Any origin free module over a PID is flat, as it turns out. So, for example, so you should actually prove this. You can't really use this. This is a statement you should try to prove yourself. So, the Z module Q is flat because it's torsion free. It's used principal ideal, but it's not projected. You can do this directly, or you can use the theorem that we're going to come to in a bit, just to make this easier. By the way, let me ask you a question. Is Q a free Z module? I mean, probably not, since I just claimed it's not projected, but can somebody argue why it's impossible for Q to be free? Right, free is the more restricted platform. Why can't Q be a free Z module? Because it wants data safety. Like when you take the smallest to move away from Q. Right. Would everybody agree that Q cannot have a basis of one element over Z, not as a Z module, for exactly the reasons that you said? If I have a basis and I call it Q, right, everything in there should be n times whatever that Q is, and you can never get Q over 2, right? So, okay, any basis that you have has to have more than one element, right? You can also show fairly easily that any 2-element subset of rational numbers is linearly dependent. And so you got no chance, right? One's not good enough, and anything bigger is linearly dependent. So Q is not free. In a similar vein, if you get it's not projected. Any questions? Let me give you this last corollary. And this, I'm going to do this without proof as well, but this basically shows the flats among themselves sort of play like projectives. Here's what I mean by that. Let MI be a family of R modules. Then the direct sum of MI is flat if and only MI is flat for all I in the base. So this theorem is exactly the analog for what happens with projective modules. Okay. Any questions? So let me ask y'all this. How many of y'all are how many of you have taken the algebra? Has anybody taken? All right. How many of you are planning to take? Okay, so I think that the next section might help a little bit with the 85-30 part, linear algebra. Because a lot of times what happens is, you get some stuff that kind of forms on matrices. The advantage to this is I'm probably doing it from a different perspective than you would see in 85-30, because 85-30, the clientele there is more of a general audience than we have in here, so they don't talk about modules. So probably, how many of you had 85-30? Okay, so in 85-30, did you do the canonical forms of matrices, the Jordan form like this? How did you do that? Did you do like, what do you call it? Generalized eigen vectors? Okay, so here we're going to do it from the point of view of modules over PID. So you're going to see this from a different perspective. And hopefully it'll strengthen up what you already know. And hopefully you'll learn something if you don't know it already. So, so here we're going to do modules. So we've talked a lot about modules. We did all this business free and projective and stuff. So now, well, we could do a section modules over a field. Some other class. Okay, so what's something that's a little bit more general than a field, but not some awful Stephen King novel? And the next sort of best domain type after a field, probably one might say is principal ideal domains, right? Like the integers, where yeah, you have things that aren't invertible, but every ideal at least is principal, right? These things are very well behaved, so let's try this. And we're going to talk about the way that modules form over CI. Modules over PID. So PIDs have structure that's not as good as it. Well, they're not as easy to fill, but their structure is well behaved enough to where we can say some positive things about modules over PID. And as an application, we will talk about various canonical forms of things that you get in your algebra, Jordan form, fractional canonical forms, and so forth. I'm going to skip the proofs of some of the results in this section because this looks all fancy, but all of you had 85-10, right? I bet you saw the fundamental theorem of finitely generated billion groups. Well, that's what this is essentially. Modules over a PID. So when you did the fundamental theorem of finitely generated billion groups, you probably ignored this, but implicit in this is what you were doing is modules over the integers, right? And that's why it works very. So you all see the theorem. If you have a finitely generated module or a finitely generated abelian group, it's got a free part, the finitely many things in it, finitely many copies of Z, and then you've got the finite part, and the finite part can be decomposed in a certain way, right? Well, that's what we're doing here. And it turns out if you look back at those proofs, some of them I'll skip, really, you never needed Z for a lot of it. All you needed was the fact that Z had was a principal ideal. Right? So with that little kind of introduction here, in this section, I will reiterate this, even though I've been teaching the class this way anyway. R will always be a commutative ring of identity. Modules are unitary. And R will usually be a PID, but I will be careful about letting you know if that's active. Okay, let's start off with a kind of a groovy little theorem here. Theorem 711. Suppose you have an R module. Let A be an R module, and R is an integral domain. Something will persist. Okay, so I have an integral domain A, R. A is an R module. Little a is an element of A. And I don't know what I was thinking when I made this letter, but whatever that is the set of R. So this is all the stuff that kills A. Sometimes I might call this the annihilator of A, but it's just everything in R that kills A. Notice that this is always non-empty because, for example, R equals equals in this set always. In fact, let me not diss poor old funny letter here, because number A this is in fact an ideal of R. B, A sub T, I'm going to define this to be all the A's in A, such that the annihilator is not zero. Notice, of course, zero always kills A. If this has something that's not zero that kills A, then it's an element of AT is a submodule. So this collection of everything that is killed by something that's not zero is a submodule. C, R, mod, this crazy ideal, and R is a principal ideal domain. Then I'll throw in a couple other little party favors. Oh, and suppose that P, lowercase p is a non-zero prime. D, if P to the I, A is equal to zero, so that is to say the ideal PI is contained in A. Then DA is actually equal to J for some J between 0 and 9. And if, take that a step further, if it turns out that that thing is generated by P to the I, then P to J A is not zero. Or J strictly less than I. I don't know about you all, but all this no notation confuses my pea-sized little brain. So I think that maybe going through the proofs of some of these might sort of help me get my sea legs, if you will. Let's at least sketch some of these. And again, I think this helps use the notation. Okay, I need to show that this is an ideal R. So let's let R1, R2 be 10. So, and well, actually, that's not right. Let's do this. Let's let X and Y be in A and R be in I. I want to show that X plus RY is still in. Notice that X plus RY times A is XA plus RYA, which is 0 plus R0, which is so X plus RY. A. So we have an I. That wouldn't be bad, right? Number B, we want to show that that AT thing is a submodule, right? By the way, let me point out that my assumption on R is that it's a domain, right? I didn't really use that. Didn't really need that first, but we'll need it later. Let's let A and B be. What does this mean? So there exists X, Y, and R, not 0, such that XA is 0 and YB. Now, to show that this is a submodule, I need to show right, that's my submodule, which AB is in if well, by the way, I guess I probably need to show that this is just explain to me why AT is not empty. Be a little careful about it. 0. Really. And I know that for sure because the ring has identity, right? So I know 1 times 0 is 0, so I'm good to go on that. Everybody okay with it? I need to show that this thing is NDA. Well, what does that mean? That this element, or not. I need to show A plus R B is in AT. What does that mean? That means there has to be some non-zero element that kills this, right? Candidates? X, Y. Do I agree with this? And there's something else that I really need to state at this point.
Since we're in a domain, X, Y is not equal to 0.
Main. Next slide, please. So. Because this element's in here, there's some non-zero thing. By the way, we've seen an example similar to this in the homework where you might say to yourself, well, is this always a submodule? Notice that I did use domain in my proof over here. Do you need domain in your proof? Well, there certainly are there certainly are rings that are not domains where this kind of thing can actually be a submodule. But there are also things that are not domains where it's not. A good example of this would be something that C6 is C. That's what I meant to say. Oh, yeah, C6 is a C6 module, so it's what I'm gonna say. Right, because the torsion elements there, aren't closed under addition. Okay, how about this last one? By the way, what do you think about the proof of this? Yeah, that's right, Jim's favorite isomorphism theorem. When you see it. So, yeah, we'll fix the tackle this one. So this one. R mod DA is equal to RA. So for number C, was defined. Remember, this is an R module homomorphism, and folks, if it ain't easy, don't do it, right? What's the easiest way? Do this. B is a surjective R module. It's clear, isn't it, that it's onto, because every little RA has pre-image little r. Everybody agree with that? And it's easy to check. It's not much fun. Everybody with me on that? So RA is isomorphic to R on the kernel B, but kernel B is all the stuff in R such that RA 0, which is precisely the definition of this. Any question on that? Let's see. Parts D and E are really specialized to principal ideal domains. And so let's prove D. Suppose that suppose PIA is equal to 0. And so what does this mean? the PI is an element of where this ideal is, and in particular, this ideal is. So this means that the ideal, VA contains PI. Everybody agree with that? And what do we know about the ideal VA? There's a very principal fact about that. So we need to uncover. It's generated by something, right? Because of the fact that. So this means this thing here has to buy, or I'm sorry. Oops. I'm not paying this one. This is the big guy. So there exists R such that PI is all of that. How does this help? What else do you know about a PID? The classical algorithm. So any PID is a right, it's unique factorization. Right, so here you have an element that's not zero, right? This is a prime factorization, affects the power of nine. So this means, a unique factorization, R is P to K, and X is, well, actually, it's going to be later. X is P to the K, and R is P to the I minus K. For some, I guess it's have to be one. This thing could be zero because A can be zero and then it's simply annihilated. Therefore, uh, and there's, we need, except I call JK. Any questions on? So, if you ever have a prime power annihilate the element A, that means the annihilating of A is the ideal generated by a power of that prime. Let's see if we can get the last one here, number E. Suppose now that and suppose here I guess that I would have to be one, I guess. Well, if P to the A annihilates J, then P to the J is one of the things that kills A, so that belongs in the ideal. Therefore, P to the J is in the I, which means that this must divide this. So there exists X and R such that X P I equals P J. This is an integral domain, so we can cancel. And so I get X P, the I minus J is equal to 1. Since I minus J is greater than or equal to 1, X plus P, that's a contradiction, because we assume it's a non-zero thing. So this establishes the last step. Okay. Questions? Okay, so let me give you kind of a big theorem that I won't prove yet, and I'll say a word about this. I'm going to deal with this theorem mostly in the finite generated case, but it's true in general, and you're welcome to use it. The general theorem that I'm going to state here actually requires the actual choice proof, and it's not terribly difficult, but it's I'd rather get on to actually these corollaries here. So theorem 7.2. Let F be a free module over a PID. If M is a submodule, then M is also. And rank M, that is the size of the basis, the size of the basis of a free module M is less than or equal to the rank of full free module F. Let me give you my Thomas corollaries here. So the first one is kind of obvious. Corollary 7.3. If R is a PID and A is an no, maybe that's not what it is. Let R be a PID. And then A, an in-generated R module. Then any submodule of A. Can be generated by M. So if you have an in-generated R module, then I guarantee you can generate a submodule within elements or maybe less if you're lucky. And final corollary, say, we'll discuss these corollaries next time. Let P be a module over PID. then P is projective. If and only. Here. So in the realm of PIDs, there is no distinction between free and projective. They all collapse in the same. Okay, any questions? Questions? All right, well, y'all have a good one, and we will see you on Friday.